Welcome back to Finite Element Methods. So this is class number 18. We were talking last time about parabolic problems, in particular the heat equation. But before we get back to that topic, I would like to take a little detour and talk about a homework problem that was assigned. So the homework problem I'm referring to is, I believe, homework 5, number 4, and it asks you to prove this particular inverse inequality, which says that it says something strange. It says that I can control a heavier H1 norm with a lighter L2 norm, but I have to pay the price of a 1 over H. Well, first note that this is not the full H1 norm. This is only the H1 semi-norm, and this is the full L2 norm. Normally, if we have functions which have zero boundary conditions, or at least zero on some part of the boundary, then we can control the L2 norm with the H1 norm. That's called Poincaré's inequality. So first of all, I want you to contrast this inequality, this inverse inequality, with Poincaré's inequality, which kind of gives you the reverse direction. It gives you this guy. So that would be Poincaré. We're not going to consider that. We're only interested in this upper bound, but the upper bound comes with a constant that is not H independent. I have to pay a price of H. The other thing that's weird about this bound is it doesn't hold for all V in H1. It only holds for V in this finite dimensional subspace we call VH. That is the piecewise um, polynomials of degree R. And we're not assuming that there's any zero boundary conditions or anything like that. We're in our simple space MR, the piecewise polynomials of degree R. Remember, these polynomials or these functions are globally continuous, and on each triangle, the restriction on each triangle is a polynomial of degree R. How do we prove this? How do we prove this inverse inequality? Again, this inverse inequality does not hold for all V in H1. It holds for all V in the finite dimensional subspace. Well, it kind of makes sense that this is true because, well, it's not unbelievable that it's true because on finite dimensional subspaces, all norms are equivalent. That's something that you learn in functional analysis. When I'm in finite dimensions, all norms are equivalent. So that's where we're going to get started. We're going to use a technique um, uh, called the scaling factor technique, or a scale factor, a scaling argument. And we're going to use the reference triangle somehow. Now, on the reference triangle, all norms are equivalent. In fact, all norms are equivalent, we know otherwise, but on the reference triangle, we're sort of in a space where the size of the H doesn't matter, because remember, the reference triangle, the H is already known to us as square root of 2. It's not a small triangle. Now, this arbitrary triangle where we're going to try to make this work is on this triangle K. But remember, this guy has a small diameter. This guy has a diameter which goes like H, okay? And in any case, on the reference triangle, all norms are equivalent for finite dimensional functions. There exists a C1 and C2 such that the H1 norm, full norm, and the L2 norm are equivalent. That means there's a C1 and C2 such that this inequality holds. Why is that true? What's true if I apply it to V hat, where V hat is a polynomial of degree R on the reference triangle. And the reason why it holds is because PR, it's a polynomial space, so it's finite dimensional. It's a very simple space. It's more simple than this space. We're working on the reference triangle, polynomials of degree R. All norms are equivalent in finite dimensions, and so we have to have this inequality on the reference triangle. In fact, I should probably write here that these norms are the norms on the reference triangle. So K hat, this is K hat, that's K hat. Okay, just to be clear. All right, Therefore, the thing that we're interested in is going to be the most useful version of this is going to be let's square this guy and see what we get. Well, if we square the full H1 norm, it has in it the L2 norm and the H1 semi-norm in there. It has in it L2 norm and the H1 semi-norm. And there's a typo there. That should be a square. Okay. Now what I'm going to do is I'm going to try to get something smaller than this by throwing something positive away. The thing I'm going to throw away is going to be this guy. I don't need it. So now I see from this inequality, I get this inequality here, which is what I want to work with. It's working with the squares of things, but it's exactly what I want. The H1 semi-norm of an arbitrary function in the polynomial space squared is less than a constant times the L2 norm of the same squared. So this constant C2, what is it going to depend on? It turns out it's going to depend on R, the degree of the polynomial, and it's also going to depend on the reference triangle. But the reference triangle never changes at all. So this is like saying it doesn't have any dependence on triangles. Okay? And this is completely independent of v hat. Doesn't matter what v hat you use. So this is the thing we have. The semi-norm is H1 semi-norm is controlled by the L2 norm. Okay? And there's no H here because on the reference triangle, what is H? H is really square root of 2. It doesn't matter. It's like we could rescale it to 1 if we wanted to. All right, now let's let V be an arbitrary polynomial on that small triangle K out here. All right. So let V be arbitrary. Then if we compose V with our transformation F, remember that's the transformation that takes the reference triangle to the small triangle. Okay, that's what we call F. If I can compose V with that, that is I do Fk first and then I do V, that defines a function, and that function is a polynomial of degree R. That's because this is an affine translation or transformation of a polynomial. It preserves the polynomial order exactly. It doesn't increase the polynomial order or decrease it. This R is exactly the same. Okay? But now we know by a formula that if I want to find the integral of f over k, then that's the same as twice the area of k. K is just some non-degenerate triangle in my mesh. So it's twice the area of k times the integral of f over the reference triangle f, well, actually f composed with f of k. So I could replace this with, say, in this one, on one hand, I can use what here? So I really want v squared here. And here, what is going to be this? This is going to be v hat squared. If that's v squared, then this is going to be a polynomial of degree 2r, right? And now this is a polynomial of degree 2r, and it's precisely equal to this. All right, so that tells me how to change my integral from an integral on an arbitrary triangle to a reference triangle. That's a formula that we talked about before. It's just the standard change of variable integration formula. So we didn't give a proof for that. Well, didn't give a detailed proof, but I told you how to get it. All right, so now let's look at this. This is what we have and what we want to ultimately estimate. So the L2 norm of v squared. And now I have this equality, so I can transform that. That's exactly what it is. L2 norm squared is just that integral. I'm going to transform that to a reference triangle calculation. But notice that this here just becomes the L2 norm squared of v hat on the reference triangle. So this tells me how I have an exact conversion between these two norms. Now I need to know how to transform this guy here. This, remember what I'm comparing. I'm comparing the H1 semi-norm with the L2 norm. So I need to know for that arbitrary polynomial v, I need to calculate its H1 semi-norm, which is the same as this object over here. This is just kind of the definition of the H1 seminorm. But we already have an estimate to deal with this, so we're not going to have to, and it's a very sharp estimate. So the estimate that we're going to use is this one here. This was also a homework problem. So we're going to take advantage of the fact that we've already proven this, but we're going to use m equals 1. So let's put in m equals 1. That gives us this. So using m equals 1, right? We just transform this into that. Right. So now what did I accomplish? I start out with the seminorm on an arbitrary triangle. I end up with a seminorm on the reference triangle of this transform function v hat. Let's estimate a few of these quantities here. Well, we know that on the reference triangle, all norms are equivalent, so that's the first thing we started out with. We said that this guy is less than a constant C2 times the L2 norm. So that is from the work we did at the very beginning. The rest is the same as what we just had up above. We just bring it down. But now we know how to transform this integral from an L2 norm on an arbitrary triangle to an L2, or sorry, we have L2 norm on the reference triangle to that of its predecessor on the triangle K, and that's given to us through this transformation here. Okay, that's a simple one actually. The hard one was this guy, but we don't need to prove, we don't need to know that exact integral. We just need to know a sharp estimate of it. So now if I replace this by this, I also get this factor. Then you just realize, well, the determinant of BK, that's equal to 2 times the area of K. That's also got a square root, so these two terms cancel with each other. We also had an estimate that said, well, if I measure the inverse of the BK matrix in the 2 norm, then that's less than H hat. That's the mesh spacing or the largest diameter on the reference triangle. That's just square root of 2, if you as you can see by scrolling back up, and then divided by rho k. So I have this estimate now for this object. I'm going to plop that in there as well. If I do that, then I get this. So now we're almost done. Let's square this once again. So square that. The c squared is just another constant. So notice that generic constants I'm just going to call c. I'm not going to worry about those. I'm not going to track their exact values from other values. And this still holds for an arbitrary function in PRK. That's a polynomial space of degree r, at most r, on the particular small triangle that I'm interested in. But now we haven't used yet our assumption that the mesh is shape regular and quasi-uniform. So shape regular means that the ratio HK over rho k, remember this is the diameter of the triangle, and this is the diameter of the largest inscribed ball. That means that the triangles don't get too needle-like. They don't get too needle-like. And if that's the case, then this ratio is always bounded above by some sigma for every triangle in the mesh and for every new mesh that I generated in this family. Next, the quasi-uniformity says that, roughly speaking, that we know that this is always equal to the maximum mesh spacing in triangulation. Well, this is saying that any diameter of any arbitrary triangle divided by h is bounded below by some c. So what does this mean? This means we know if we multiply both sides by h, or all sides by h, we get h here and an h here. This just says that h is bigger than hk. Well, that's by definition, it's the maximum. So the real meat is then this guy here. H is bigger than QC times H, where QC is some number greater than 0. So we can add that, some number greater than 0. Okay, and this holds for any triangle in the mesh and for any mesh that I want to generate in that family of meshes. Okay, so now so we have this. Let's put this together. How do we put this together for all the triangles in the mesh? Well, here's how we do it. Let V now be an arbitrary element from MR. So now when I restrict V to any particular triangles, it's a polynomial of degree R. But globally, it's just a continuous function. It's not a polynomial globally, necessarily. But notice that I can write this H1 seminorm over the whole domain omega. If I square this norm, I could write this as the sum over triangles of these H1 seminorms squared over individual triangles. So what this means is if you're doing an integral over all omega, and I can break that integral into subintegrals over the smaller mesh pieces, the triangles. That's all this is saying. You're converting a big integral into integrals. Yeah, and basically it follows from this fact. If I have an integral over the full domain of something, dx, then that's equal to the sum over triangles in the mesh, integral over k, dx. That's where that piece of information is coming from. Let's see if I can make some room for that. So I hope that makes sense. Okay, I can put anything in there that I want. So I'm just breaking an integral over the large domain into smaller integrals over triangles. Okay. So we're just going to start here. I guess this kind of doesn't fit, does it? Let's see. Let me move this. I'm starting a long calculation and breaking it in the middle. So let's do it this way. There we go. That'll work. So here's where we're starting. We're starting with this H1 seminorm. We're breaking it into seminorms over triangles. Of course, it's squared. You have to use the square to get that. Then here, if you look at this quasi-uniformity, what does it say? Well, quasi-uniformity, if I multiply both sides by h, then I get, or all sides by h, I guess. Just cancel that, multiply by h. I get an h here. And so this inequality implies this one. But now this tells me that the reciprocal 1 over hk is less than um, the quotient 1 over CQH. Okay, that implies that. It's like saying if I have A less than B, then 1 over B is less than 1 over A. All right, so that's just a fact that we're breaking out in the middle. The actual inequality is continuing from here. So what I'm going to do is I'm going to use the inequality from above that I just proved, this guy here. We're replacing the H1 seminorm with the L2 norm, but we have to pay this penalty here. Okay, no problem there. Now, to get rid of this, I'm going to multiply and divide by hk squared. Hk squared, the reason why I'm doing this is because if I get a ratio of hk over rho k, then I can use quasi-uniformity, or sorry, shape regularity. So I take care of shape regularity. This is going to be what? This is going to be like sigma squared. Should be sigma squared. And then what about this guy? Well, what's left is 1 over hk squared. 1 over hk squared is going to be less than 1 over cq squared h squared. So that guy. So I'm replacing that by this calculation here. And now once I have these numbers here, notice that they're completely independent of k, so I can bring them out. Once I bring them out, then I can rewrite what's left as just an L2 norm squared over the whole domain. And now I'm working in that variable v, back to variable v. And what's the constant that I have out front? Well, it's just some amalgamation of constants. These are all constants over h squared. Now, to get the final estimate, I just take the square root. Take the square root and you get this estimate here. And this is what we call the inverse inequality Well, it's really a specific type of inverse inequality. It's the one involving the H1 semi-norm and L2. So it's saying that if I want to bound this weightier norm by this lighter norm, I have to pay the price of a singular term. Why is it singular? That's important. It's singular because H usually goes to zero. So as H gets smaller and smaller, this guy goes to zero, whereas these guys may stay stable. So this is becoming a singular constant. This is becoming a very large constant. It's saying that ultimately it's really difficult to control this norm, this weightier norm with this less weighty norm. Okay. Now, if I want to go the other way around and use Poincare, then it's perfectly fine. I can always use this norm to control the L2 norm using Poincare. But I'll leave that to you. All right, so that's homework number 5, problem number 4, proving an inverse inequality. And right, so why did I do that detour? It's good because it brings together lots and lots of nice facts that we already learned, and it puts them together in a very beautiful way. Well, let's go back to a review. We were talking last time about finite element methods for parabolic problems. I'm going to run through this first part quickly because it really is a review. We're looking for a solution U to this equation with this boundary condition and this initial condition. So this is what we sometimes call initial boundary value problem. Initial boundary value problem. It has a time dependence. Okay, it has also spatially dependent variables. So that's expressed through this expression here. It is dependent upon space and time. This f is given information. So typically that's a continuous function, or at worst it could be a function from this function class L2, 0t, L2. We explained what this function class meant or looked like last time. V is typically just some L2 function, some initial data. And then if we want to express a weak form of the problem, how do we do that? You integrate by, you multiply by a test function, integrate this term by parts, and you get what's called a weak formulation. We discussed this last time. So weak formulation, or sorry, weak solution to the diffusion problem is one for which U is or has this class of regularity. It is an L2 function, 0t into H01. It's also, U is weakly differentiable in time, and its time derivative lives in a similar space, only it had that weird negative index space. So this we said by definition was just equal to the dual space of H01. So that's from last time. Such that for almost every t and for every test function phi in H01, this is a spatial only test function, then this equality holds. So this is what's really usually called the weak formulation of the equation. I forgot in my notes last time, and I corrected the notes from chapter or from lecture 17. This is now lecture 18, to add this part. And it says basically that as I take time down to 0, my U, my solution, agrees with the initial data. So what this is really saying is that U satisfies the initial conditions, period. Okay, so this is just the fancy mathematical way of writing it. Last time we proved this result, but we did that in a kind of rigorous setting. And I saw a lot of confused faces when we were talking about it later. And so what I promised to do and what I'm going to do this time is we're going to give another proof of this, but it's going to be a hand waving, what is called a formal proof. And a formal proof simply means we're going to assume U has the correct form of the solution, um, but that we can do basically every manipulation that we usually do without thinking about it. So what do I mean by that? Well, I'll show you in a second. So the two estimates that I want to prove are what we called energy estimates. And the first one says that this norm of the solution is bounded by this information here, which is data. And this norm of the solution, again, this is a solution, but now we're integrating that. So it's an integral type of norm in time that is less than the same initial, or sorry, the same given data. Okay, so this is the initial condition and this is the forcing function on the right-hand side. Or I should say it's f in the integrand is from that. If we have additional regularities of the solution, then we can show that we have a similar sort of what are called energy estimates of this type. And so last time I tried to prove this rigorously, and today we're just going to give this a formal argument. And what do we mean by that? Again, what it means, formal means form. We look at the form of given solutions and we assume that all the manipulations we want to do, as long as they're standard manipulations, like the derivative and the derivative in space and time interchange or derivative in an integral interchange, et cetera, et cetera. We're just going to assume that everything, every type of formal calculation we want to do goes through without a hitch. So let's start with our strong form of the solution or the strong form of the problem. So that is not the weak form, right? It's just assume everything makes sense. We're going to multiply by u. Multiply that by u and integrate. So if I multiply by u and integrate, I precisely get this object, right? This guy here, I'm going to integrate that one by parts. I'm going to throw this spatial derivative. These are spatial integrals, by the way. I'm going to throw this spatial derivative from the Laplacian u over to this guy on u. I'm going to keep one derivative here and then I'll have one derivative here, but that changes the sign. What I get is nabla u dot nabla u, or in other words, this integral here becomes that integral. What happened to the boundary integral? The boundary integral vanishes because I'm using that u is equal to 0 on the boundary. Okay, I'm using boundary conditions. Also, I'm going to convert this integral here by noticing that if I'm allowed to interchange the integration and the time derivative, then this integral here is just 1/2 times the time derivative of the integral of u squared. So I'll let you convince yourself of that. We used that fact last time, but it's if everything interchanges properly, then it's clear that that's true. As I said, that after doing integration by parts, that integral becomes that one, and this one I didn't change anything. Right, so notice now that this guy here, just in that box, is an L2 norm of u. This is an H1 semi-norm of u, and so I've just converted those directly. This guy doesn't change, and so we'll bring it down. That's our notation for the L2 inner product. Now we're going to use the Cauchy-Schwarz inequality on this guy. So it gives me an L2 norm of f times L2 norm of u. I'm going to use Poincare next to bound the L2, the weaker L2 norm by the weightier H1 semi-norm. Okay, so that Poincare allows us to do this as long as the boundary conditions allow it. And the boundary conditions are perfect for the application of Poincare because we said the boundary conditions are just 0. Next, we use an algebraic geometric mean inequality. Basically, this is the same as last time. Basically, we're going to try to split this into roughly 1/2 this number squared plus 1/2 this number squared. But we're going to, when we do that, we're going to divide this, or sorry, multiply this term by a c and then divide that guy by a c. The reason why I wanted to do that is because I want to get rid of the c there. And I don't care how big the constant gets in front of the f term. Once I divide by that c, notice that this coefficient here is just a half, and I have coefficient 1 over on that side. Perfectly fine to subtract the like terms from both sides of an inequality. And so that gives me half, half, and half. But I can then multiply by a 2, and that gives me this equation here. So I hope everyone sees how to get from this equation or inequality, I should say, to this inequality. And now I've just made c squared, I just rewrote that as c. Okay, generic constants, I'm always just going to revert them to c whenever I want. Now let's integrate this quantity in time from t equals 0 to an arbitrary s in 0 to t. Okay, so each term gets integrated 0 to s, 0 to s, 0 to s. Okay, nothing really changes, just integration. Then I notice that this is a perfect derivative. Perfect derivatives, what happens with perfect derivative? If I integrate them, then I just evaluated the two endpoints and take the difference. Okay, that's that term. And the fact that I have that the weak solution satisfies the initial conditions perfectly, then this is going to just be V instead of U0. This I don't know what it is, but that's okay. Now the V term I can move to the other side, right? I can move it over to here. So I'm going to write that all as one term. I've got this at an arbitrary time s. This integral up to an arbitrary time s is less than data over here. Now, I'm simultaneously going to take this integral here. Actually, I've already done it and I forgot to mention it. This integral here, 0 to s. To go from this step to this step, I'm just going to make that larger by increasing the upper limit of this integration from s to t. And that makes it larger, so it's still, this all still holds. So for arbitrary s in 0 to t, I have this inequality. But notice now this left hand or right hand side, sorry, is independent of s. Okay, so I'm going to use that to my advantage. Let's throw away this term. And what I mean by throwing this term away is let's bound this below by just this term here. Okay, so I'll bring that over and I get rid of that guy. Then that's just this inequality here. Notice everything else is on the right-hand side and preserved. But now notice that this is independent of s. I can take the maximum of all values in s. So that's what I'm going to do next. Take the maximum. So this is like an upper bound for all of these. And so what is the maximum? The maximum is like the least of the upper bounds, right? I could use, of course, soup, but we know that this is going to be bounded and that this has a maximum because it's a continuous function from 0t to L2. So this maximum actually exists. So this max has to be bounded above by this information here. And that is exactly the first estimate that I wanted to show. This is saying that this energy, quote unquote, never rises above this value. Now, by a similar argument, I can throw away this term and keep only this term, and then take S to be its maximum value, which is just T, and that argument gives me this inequality. But this inequality is exactly what I wanted to prove for the second estimate, so we're done. Okay. I wrote them together as one, but you don't have to write them together in one estimate. Now, let's prove the second set of estimates. Again, we're going to start with the strong form, but this time we're going to multiply through by minus Laplacian u. So make sure you understand, we're just using the form of the equations. We're not using any sophisticated PDE theory or anything like that. It's simply the form of the solutions is going to tell us the form of the equations is going to tell us what to do. So I multiply by this test function and integrate. I immediately get this in my second term, but I have something wonky in the first term. Nothing I can do about this term. But I'm going to integrate by parts, throw this derivative over to here, and then I can argue that, well, because we're just in formal land where as long as it makes sense, it can work, we're going to interchange the nabla and the time derivative to put the nabla against the u here. So if I integrate this term only by parts, then I get this, okay? Arguing again that I can interchange time derivatives and space derivatives, and then ultimately I can bring the space derivative out front of the integral. So If it comes out, then it looks like this. It changes from a partial derivative to an ordinary derivative. This term here is just the Laplacian of u L2 norm squared. And this term here, I'm not going to change, minus the L2 inner product of f against Laplacian of u. Now, again, use Cauchy-Schwarz, break this into these two, into product of these two terms. Then we're going to use the algebraic geometric mean inequality. So algebraic geometric mean. Not the special form that we used last time, but just the basic form. Using the basic form, we're just going to split this into a half f L2 norm squared and 1/2 L2 norm squared of Laplacian u. Now you notice that this comes with a coefficient of a half, and this is a coefficient of 1. So I'm going to subtract from both sides this number, or in other words, move a negative over there. Then I get halves on each of the terms. And then I multiply by 2, and that gives me this inequality. So now we're back to what we had before, or similar to what we had before, and the analysis becomes simple. Integrate from t equals 0 to t equals s. When I integrate this perfect derivative, I just evaluated endpoints and take the difference. If I do that, then that's what I get on integrating that. And what I get on integrating this is that. When I integrate this term, I have that, and I'm just going to bump this s up to its largest value, t, and I'm going to stop there for that. Okay, what's next? Well, now we want to take this guy and move it to the other side. So move that v to the other side. Why are we moving it to the other side? Because we want to put everything which is given data on the right-hand side and everything else on the left-hand side. Well, now using the same ideas as before, I can throw away this term first and bound this below by just the H1 seminorm. Then I can take the maximum of that in S. This side didn't depend on S, and so we have that as a hard and fast bound, upper bound, for this, which I can consider as the supremum. What about this term? Well, this guy here comes just by analyzing this part of that. I can throw this guy away, no problem. And I can take this bound up to t, or this upper bound up to t. That gives me that. And that's exactly what I wanted to show for my second estimate. So those two are done. So you can see that this may be much easier for you to understand and see. However, it's not rigorous. What we did last time was the rigorous arguments behind that. And even then, we didn't really provide all the details. So just be aware that when I'm doing manipulations like this, I might be doing something which is not necessarily allowed unless I have really smooth solutions. If I'm working only with weak solutions, they're not that smooth by definition. And so I may not be able to carry out all the manipulations that I want without some care. So just be careful. Now, let's look at these estimates that I just proved. Okay, let's go back up and I'll look at the two together. So there they are. So this is the first estimate, the kind of low regularity estimate, and this is the higher regularity estimates that we get. We had to assume higher regularity to get them. All right, so what I want to do first is I want to look at the case, the special case where f is equal to 0. Then all of these integrals go away. There's no initial data. So let's look at that. In particular, let's look at this guy first. What happens whenever f is 0? Well, then this says that this norm, this energy of the system, is bounded above by this energy of the system. So let's have a look and see what that says. Well, if f is 0, then I only have that v part, and I have this remaining. Right, so that is in the case that I have the lower regularity for the weak solution. If I have the higher regularity for the weak solution, then I have this. And I believe I have a typo here. I think this should be an H1. see, what is it? Yeah, it's an H1 semi-norm. There we go. Okay. I could make this H, right? The H01 norm is the same as the H1 semi-norm, but let's just standardize. Yeah, I'll go back to what it was. That'll standardize it just fine. But it still had a typo on it. There we go. Okay. Now, in this case, it's also pretty easy to show just by going back through my analysis that, in fact, for every T1 and T2 in 0 to T that have the following ordering, T2 is bigger than T1. What I can show from my analysis is it's actually fairly straightforward to do this. In fact, I think I'll make this a little exercise for homework. That's a good one. And where it comes from is in the step in this step here. Instead of integrating from 0 to S, what if I integrate from T1 to T2, where T2 is bigger than T1? Well, in that case, I get U of T1, or sorry, U of T2 minus U of T1 there. And all the rest of the stuff I can get rid of and throw away. And so what happens is I can put this guy over on the right hand side, leave this guy on the right. This guy will go over to the right hand side. This stays on the left. Okay, remember that's with T1 and T2. So I claim it's not too hard to show using that same proof technique or a similar one that actually I have this. So what this is saying is I can think about the L2 energy or the L2 norm squared as something like an energy. And what this estimate is saying is as long as F is equal to 0, then this number is going down and down and down and down in time. That's what we call dissipation. So basically I can plot it on an axis like I would plot anything else in time. And what this is saying is the L2 norm, it could have little plateaus and stuff or almost plateaus, but basically it's going down in time. Okay. That's what we call decreasing. So that in that sense, it's like what's called a free energy of a system. It's being dissipated, it's going down in time. And so that's why we call estimates of this type energy estimates. Let's see if I can move that. There we go. So this quantity is getting dissipated in time. And a similar sort of analysis shows that the H1 semi-norm of U gets dissipated in time. Whether it's the square or the square root of that, it doesn't matter. Usually we work with the square, but this is another expression of an energy, and this is a typo too, right? Because that should just be H01 norm. So the H01 norm of U is also dissipated in time. That's because for any T2, its value is less than the value that we had at the earlier time T1. So that is something like the picture here. If I color this as T1, that's the early time, and T2 is the later time, I can see that the value at T1 is bigger than the value of the later time T2. This holds for any T1 and T2 in the interval. And so we call this an energy dissipation. And we call the estimates that we derived energy estimates because they look a lot like free energy dissipation estimates that we can prove in non-equilibrium thermodynamics. All right, let's use the estimates that we have that we've derived to deduce what's called a continuous dependence on initial data. Suppose that I have two solutions that solve two different problems. Now, we're going to assume that they both have the same right-hand side forcing term, F. So there's two solutions, I equals 1 and 2, to solve this problem. Now, we're going to assume that they have different initial conditions, but they have the same forcing function. Different initial conditions, but the same forcing function. Okay? So what I can do is, if I assume that I have both the solutions that satisfy this problem, even if they're weak solutions, what I'm going to do is subtract. If I subtract those two, one from the other, I'm going to call that difference E. Now, this isn't really the error, it's just the difference between those two solutions, okay? And the equation that that is going to solve is this equation. So that's because of linearity. The difference of the two solutions has to solve what's called a homogeneous heat equation or a homogeneous diffusion equation. Homogeneous because there's no right-hand side. Homogeneous Dirichlet boundary conditions. And the initial conditions are not homogeneous. They are V2 minus V1. Okay, and actually, I guess that means, let's see here. I have a typo because if I've defined, I think the easiest way to do this is make sure I define this as E2 minus E, or U2 minus U1, and then it all works out. Okay. Now, using the estimates that I derived above, since this guy is an L2 function, this guy is homogeneous Dirichlet, and the difference of two L2 functions is an L2 function, well, then this, what I'm going to call the error problem, is the same as the original problem, except it's got this term as being homogeneous. And so that's like saying the F term is 0. In that case, then the estimate we just proved states that the maximum, uh, I called this S before, but we can change it back to T. Let's make some room for that T in there. I like to emphasize that it depends on T. Okay, well, that's the same as this max here. And our estimates are energy estimates that we derived before, so that this has to be less than the initial data. Well, the initial data here is the difference of two initial points. If I have additional regularities, then I have this type of estimate. The max of E in the H01 norm squared is less than the difference between V1 and V2 in the H01 norm squared. All right, so what this says is it's called continuous dependence. That means that if this distance here, the distance between these two functions, or in other words, if the two functions are really close together, V1 and V2, then this says that this difference in solutions must also be small, right? If this is small, then that smallness has to show that this is small. Okay, so that's what we call continuous dependence. It means that if I change the initial conditions by just a little bit, the solution that solves that equation only changes by a little bit. Okay. And the same with additional regularities. If I change this by just a small amount in the H01 norm, then the difference of the two solutions changes by a small amount in the H01 norm. Also, this theory guarantees that weak solutions are unique. How can I see that? Well, suppose that U1 and U2 solve exactly the same problem with the same F and the same initial condition V. So this is like saying V2 equals V1. So their difference has to be equal to 0. So that says that the difference equation satisfies that guy. Well, our estimate tells us that this difference here is now 0. And so it says that the maximum of E is equal to 0 because it's bounded below by 0 and bounded above by 0. So it has to equal 0. Well, this just implies in this case where V1 and V2 are the same, that my error or my difference between the two functions is also 0. So this tells me that I have unique solutions. Okay, if I suppose I have two, then I get two distinct ones, then I get a contradiction. So the theory above, this theory of continuous dependence, also has this added feature that it proves that solutions are unique. All right, the next topic we want to talk about is how can we do finite element for parabolic type problems. We're going to answer basically the idea is ultimately how do we generate approximations of the parabolic problem? Well, we're going to first stick to what's called a semi-discrete approximation theory first. And that is we're only going to think about the finite element method as working in time, or sorry, working in space. So how did we do that before? Well, we said it's best if we think about omega as being a polygonal domain. Let's consider it to be so in R2. Suppose that VH is our finite dimensional favorite subspace of choice. Let's see, is this? I think it was 0R, wasn't it? Um, so that's the finite dimensional subspace we're going to choose. Piecewise polynomials of degree R with 0 boundary conditions. That is a subspace, a finite dimensional subspace of H01. Of course, we can generate nice bases for that. We talked about how to do that, in fact, using the hat functions. So here's our approximation strategy. The Galerkin approximation of the weak form of the diffusion problem is defined as follows. So we're going to start from the weak form. That makes sense. We're going to look for a solution UH, which we're going to think about as functions mapping a time from this time interval 0 to t into a function of space. So for each time that you give me, I'm going to give you a element from my finite dimensional subspace M0R. And it's going to be of the following form. I'm going to, what would I normally do in this case? Well, I would have coefficients for my solution U multiplying my standard basis functions, my hat functions, phi I, from I equals 1 to n r 0. But now I'm just going to say, well, the way I'm going to make this finite element approximation work for the parabolic problem, let's let these coefficients be dependent on time. So let's let them change in time. So that works. That gives me a pretty nice method. So what I'm going to do is I'm going to put that into the weak formulation. Where did U go normally? Normally U was here and here. So instead of U, I'm going to put UH in there. And that gives me this approximation, 18.1. It holds for all test functions psi. Psi is not in H01, but it's going to be from the finite dimensional space VH equals M0R for all t in 0 to t. It turns out that this is nothing more than a system of ordinary differential equations, which I'm going to prove to you momentarily. This is just going to be a system of ordinary differential equations. And it's going to obey this initial condition. The initial condition is, well, first of all, I need to put the initial data into the subspace VH. The way I'm going to do that is I'm going to use a projection. Projections put continuous functions into the finite element spaces. So how could I do this? What projections do I know so far? Well, one of the projections I know of so far is the interpolant. So I could use the interpolant as the projection, which puts my continuous V into the finite element space VH. And then all I'm going to demand is when I look for this solution, its initial data is, remember this guy, this is a family of functions in the finite element space, right? Parameterized by the time parameter. For each time parameter I give you, you're going to give me a finite element function. Whenever UH is equal to 0, it should be equal to VH. What was VH? VH is my projection of V into the finite element space. And that's all I need to define my finite element approximation. It's called semi-discrete because time is still continuous in this case. Now, by the way, just for your recollection, a projection operator is some operator which is going to take this function from a continuous space like L2, an infinite dimensional space, and it's going to push it into the finite dimensional space. It should also be linear. And of course, a projection is one where if I apply it to itself, I just get the thing back. So in other words, once it's already in the space, then an application of that projection operator again is like the identity. We're going to discuss some possible forms of that operation below and in our discussions. Now the definition above here, I can make a nice little replacement instead of using these from the finite element space. I can replace those. Well, instead of being arbitrary, I can replace that with the basis functions. So I can, instead of having that be generic, let's just replace it with phi I for I between 1 and n r0 for all t. So this 18.3 is entirely equivalent to 18.1, and I still have to apply the initial conditions 18.2. Well, let's see what this looks like. Let's show that in reality is just a system of ordinary differential equations. So to show this, we need a couple of definitions. Let G be the square matrix with entries Gij, the square matrix with entries Aij. This is just the standard good old-fashioned friendly stiffness matrix. And so remember, the ij element of the stiffness matrix is just A phi j phi I. What is this matrix? This matrix is new and it's called the mass matrix. So this guy is called the mass matrix. And this guy is stiffness. Okay, this one is new. You've never seen that one before, most likely. And this one is the old tried and true stiffness matrix from the past. Let's define this vector function, which takes a point in the time interval t and it maps it to a vector. So this is like a vector which is changing in time. That's all it is. We're going to define it in the following way. F of t is just going to be the collection where fi is just equal to the L2 inner product of f with phi I. Okay, why is it changing in time? It's changing in time because f changes in time. It changes also in space, but it's changing in time. And so when we take the L2 inner product of this spatial function with this spatial function, I still get a function of time. Okay, and that's going to be the element fi of t. Finally, let's define v as being a collection of components vi. Of course, it's in R and R and R0. This is the length of the vectors. Where vi, the component, is just equal to vh against phi I. Okay, so vh against phi I. So let uh that we defined above be a strong ODE solution to 18.1. It just means, well, this has a meaning, but just think it satisfies that ODE above. How do I know that that's an ODE and not a PDE? How do I know that this is an ODE and this is an ODE, but not a PDE? Well, it may be a little hard to see, but that is the case. It'll be easier to see once we're done with this. But in any case, we're going to start off with this as a solution subject to the appropriate initial conditions. Then what I'm going to do is through a couple of transformations, show that the vector, let's see, U is just a collection of the UIs. Okay, that's the solution that I just said exists. It's a collection of those coefficients from the basis expansion of that U. Satisfies this system of ordinary differential equations. So this is usual time derivative here. So this is the time derivative of a vector function of t. That gives me a vector. I'm going to multiply that by G. G is called the mass matrix. And add that to the stiffness matrix times the solution vector. And that equals that F vector. Okay? And the initial condition is just going to be G of U is equal to V. Or in other words, I could take this guy and I could invert it and throw it on that. U0 is equal to G inverse times V. All right, so what I'm going to try to show is that semi-discrete finite element method that I just cooked up here really can be written in component form in this way. Okay, solves this problem with this initial condition. This problem here, I hope you can see, is clearly a system of ordinary differential equations. So it's a fairly standard form. Okay, and so I just need then to show you how I get from 18.1 and 18.2 down to this thing 18.4 with the initial conditions 18.7. Okay, so let's start with our simplified. This is what's called the Galerkin formulation, 18.3. It's simplified because I've replaced the test function, which was arbitrary before, by phi I. Okay, that's easy enough to show that I'm allowed to do that. So we're going to start with that. We're going to insert, I said insert, that should be insert, inserting 18.5 into 18.3. So we take this expansion and we're going to put it into 18.3 and let's see what we get. Well, if I do that, I can pull out the coefficients with respect to u because don't depend on space. When I do that, I get a time derivative. Why do I get a time derivative? Well, let's look at 18.3. I'm taking the time derivative of that thing which I'm expanding like this. The time derivative doesn't see this guy. It only comes on this and sees this guy. But once it hits this, it's no longer a partial derivative. It's just an ordinary derivative. So I get time derivatives of that. That's just these terms. I'm going to pull those out of my inner products because, again, they're not dependent on space. This one, this is just the standard formulation that we've seen before. If I put in that expansion into that term here, then out pops the stiffness matrix, right? Or these terms, which are the coefficients in the stiffness matrix. And of course, the right-hand side didn't change because it doesn't depend on u at all. Okay, there's nothing. The UH is only in these two positions. Once I put that expansion in there and do some fairly basic manipulations, I just get this. But now I come back and I examine this term and this term. This term, these are just the components of the stiffness or of the mass matrix. These are just the components of the stiffness matrix. So I can put those in there, here and here. Now, it's pretty clear that these are just the component forms of the thing that I want to show, just this right here. So picture that. That's just the component forms of 18.4. Should be 18.4. Component forms of 18.4. All right, now that's great. So we're almost done because now all that we have to do is show that the initial conditions are satisfied. All right, so what is 18.2? 18.2 was the initial condition. Let's scroll back up and have a look at that. There's the initial condition I have to satisfy. Okay, this is just for some projection. I don't know what it is or care what it is for right now. All right, so now what I'm going to do is I'm going to multiply by the basis function phi I for 18.2, and I'm going to integrate in L2. All right, so what happens when I get that? Let's insert then the expansion for UH. Okay, insert the expansion. We're going to move this guy to that side and this guy to the right-hand side. So this goes to the left-hand side, and we're just going to move that to the right-hand side. I've inserted that expansion for that in here. All right, and what I see coming out is I can pull out this, I can pull out the sum, and what I'm left with is the components of the mass matrix, Gij, that's from these two terms in the L2. Now, if these two were in the A bilinear form, then I get the components of the stiffness matrix. If it's L2 bilinear form, or inner product, I just get the components of the mass matrix. This is unchanged, moves out. The sum came out. So what is this? This is just the mass matrix times the vector of solutions. Okay, and now, well, in total, what this is just the ith component of that matrix vector multiplication. And so now what we've shown is that this is equal to the components over here. Is that exactly what we wanted to show? And it is, right? Because this VI, right? This VI is defined in this way. The ith component for that vector V is exactly that. That's what we have here. So this is just VI, right? And then the conclusion is that, well, you just have G times U0 equals vector V. We can conclude that right away because we know that this is just VI by definition. And that's exactly what we wanted to show. So I can erase that, we're done. And that's it, there's nothing more. So let's review what we started with. So we started with a definition that may or may not have made sense. So we said, let's do the Galerkin approximation of the problem in this way. We're going to use the weak form, but instead of looking for solutions from the continuous space, let's look for solutions of this weird shape and form. Put those in, right? We use for test functions anything in VH, but we argued that, well, I could replace that V or that psi with, instead of being arbitrary function, I could just replace it with the n basis functions, phi I. This is the form that we want to start working with. So then if I put in the form of this solution, what it is exactly from here, and start doing some manipulations, introduce these definitions. This one we've seen before, this is new. Then I can show that my Galerkin approximation results in this vector differential equation. But this vector differential equation is just a linear system of ordinary differential equations. By the way, the matrix G, we can show, and we will talk about this next time, is an invertible matrix. So I could multiply the inverse by the inverse of G on the left in each term, and then I just get something purely for U prime. And in that sense, it may be easier to see that this is just a system of ordinary differential equations. In fact, a system of linear ordinary differential equations, for which there's many techniques to solve. And so the next step that we would do if we wanted to approximate this problem is maybe we could solve that exactly. However, it's not likely that we could. And so if we can't solve it exactly, then we'll probably resort to using some of the methods that we learned from 572, like a Runge-Kutta method or the trapezoidal rule or forward Euler, backward Euler, etc. And so that's what we're going to focus on next time. We're going to focus on making direct approximations of the solutions to this differential equation to get a fully discrete approximation methodology for solving the diffusion problem. So that's where we'll stop, pick up there on Thursday. And you can turn your cameras on and I'll take your questions.